This is going to be more of a potpourri because we've had very few on-topic questions and a lot of off-topic questions. So good afternoon and welcome to the Winter Spring 2021 EM course. Today, we normally would be talking about Fourier transforms and image formation, but we have opened it up to everything that was covered in the first month. The main idea is that this month is on the EM fundamentals. We want to cover all the basic knowledge such that when we move to the other modalities and other sections that what we call foundational knowledge is already conveyed, or if there are any concepts that are burning questions, we get to them so you don't have to wait, let's say, to the single particle section, which is a month away. Something that we don't have is a class theme. If you were here earlier before we started the class, we were seeing how can we get Bernie going. So we don't know. I think I've seen a reconstruction where the TM domains are replaced with Bernie sitting in a chair. So if you want that to be a meme, that's fine, but we've had no suggestions. Otherwise, you'll just have to get boring old starter slides like this for our class. Something that we have been working out for something that we're struggling every year is that there have been several different registrar issues to getting the class registered. To confirm, someone from Columbia has registered using this course number, so it has to be in the registrar. I don't know if other universities are having problems, but we've been working through it, partially because the start date of everyone's school semester is different. So we started this course a couple of weeks before some universities actually start their spring semester. And now, at least at Columbia, I think we've gotten the registrar situation settled. If not, let us know. The point person at Columbia is Joachim Frank. So the instructor that you would find in the registrar would be under Joachim. As we move further along, what we try to do this first month is to give you some idea of how this flipped classroom goes, because next week we'll go more into different modalities of EM. So next week, we're going to go on to our EM crystallography section. Bill Rest will talk about micro-ED and 2D crystallography. And the week after, Hernando will get into helical reconstructions and how we use a lot of 2D methods earlier on to really push EM. Something that Micah is starting up, we've gotten a lot of last minute responses. So every time I tell Micah, okay, here's the email list, someone else replies, can I be on that journal club? And what that means is that this Wednesday, we won't have a class because we're just still trying to sort out how many people actually want to sign up for the journal club. So the journal club proper will start in February. So there won't be a class on Wednesday, but that gives you extra time to think of really good questions to ask our guest lecturers. And so hopefully, before Friday, you can give me those questions such that I can give the lecturers a heads up on what people would be asking. So right now we have opened the floor for questions. I received quite a few last minute, meaning like literally 5 minutes ago questions. So I tried my best to just add a few slides on there, but if you have other questions beyond image formation and just general Cryo EM questions, well, this is the time to ask it. And we want to make sure that this is interactive and we answer the questions that you really have. So there was a question that came out and they were seeing papers saying, I go beyond Nyquist. So what do we mean by Nyquist? So there's a physical pixel size in our sensor, our camera that we take pictures of, and our microscope has a particular magnification. So you would say, okay, in light microscopy, your resolution would be, well, how can you differentiate 2 points from each other, right? So, there's a point spread function and you can take a Fourier transform of that and you can get your CTF, et cetera, or aberrations from the microscope. But the idea is like, well, then what is your resolution in EM? Well, given that most of our detectors are now digitized. Before it was film, and you would say, like, well, the film grains, like what's the size of the film grain when you had an electron hit, what actually registers as a count. and then you had to scan it. So then what was the scanning resolution of it? So like modern day, what we think really of is that we have a camera with a physical pixel size. When we have an electron event hitting that pixel and that pixel lights up, well, our resolution would be how do you distinguish one electron event from another, one pixel from another. So your physical pixel size, if it's, let's say, 1 angstrom per pixel, then you would think of your Nyquist level. Well, if you can tell an angstrom from another angstrom, like a 2 angstrom Nyquist limit. You wouldn't expect, if your magnification gives you a pixel size of an angstrom, to get better than a 2 angstrom resolution structure. Well, then how would you have a 1 angstrom physical pixel size and get sub 2 angstrom reconstructions? What does that actually mean? Well, that goes back to what we were talking about yesterday with super resolution for cameras, where if you can use super resolution techniques to not just count that pixel, that electron event in that pixel, but what quadrant of that pixel, then you go beyond your Nyquist limit. So then you are not considering that whole pixel lighting up. You're thinking one quadrant, let's say the upper left of that pixel, and then you count that as 1, and the other 3/4 of the pixel are not an account. So then that's great. So then you can use like light super resolution techniques, and you can go beyond Nyquist. How does that work? Well, there's a mode called super resolution in the Gatan space where you just do that. You fit. So if an electron is hitting a quadrant, then you fit that. If it's hitting a quadrant, it'll light up the neighboring pixels, and you fit it to know, okay, what quadrant is that pixel hit? You make that a 1, and then you divide 1 physical pixels to 4 virtual pixels, and then you can go beyond Nyquist. And so there's some estimation there, there's some cheating there. It's not completely accurate. How well can you go? Well, I would recommend that if you're interested in learning a lot more about EM, we have 2 very good mailing lists. For example, CCP-EM and 3D-EM. And there was a discussion on this. If your physical pixel is, let's say, 1 angstrom, and then you go super resolution and you get a 1/2 angstrom per pixel, what would you expect ideally to go if you wanted to go beyond Nyquist? And roughly 150% is how far you can go. And you can read papers on this. There's one paper that I pointed out earlier that was interesting. And this was when they were using a K3 in super resolution CDS mode. They went 149% Nyquist. So I believe the 150% here, which they cited citation 3, is really this paper. And they went in super resolution mode doing that, going all the way there. And if you want more information about these papers, either Eugene or Micah will in the chat just quickly type out what I'm just referring to. How searchable are these mailing lists? Okay, that is a good question. That is something that is it indexed? Yes, it is indexed. Is the search very robust? It may be hard to search a topic that was discussed a couple of years ago, because if you don't have the exact search terms, you might not pull up the issue. For this, you can see this was coming from my email, and I remembered there was something like Nyquist and like Fourier binning, and I pulled this really quickly out of my email search. But if you were to go to the listserv, I don't know how. It might be easy. I just don't know. I haven't tried that. So that is something that I'll leave to someone else to figure out how easy it is to really go through that.
Oh, so CCP-EM has become better indexed. Sorry, I mean 3D-EM has become better indexed. You can do a Google search. If you add 3D-EM, it helps. And I think they even have a search on their page. I'll look for it now and put it in the chat if I find it. CCP-EM is a little less well indexed.
So Micah, have you ever gone beyond Nyquist?
No, I have never collected anything that went, below 2 angstroms. So never had much use for super res in my own sort of personal projects.
Right.
Test samples, sure, but
So something, you know, what I'll whoops, maybe I didn't want to stop sharing. I wanted to stop screen share and I'll add something. So what are SEMC's standard data collection parameters? Okay, so just in case you can't hear me, I'm going to type it out concurrently. Normally, we're on the Titan Krios. We use a Gatan imaging filter. Currently, we have the initial generation ones. They're the bioquantums. The biocontinuums I hear are a bit more stable. We have a Gatan K3 camera. So I'll get into cameras in a little bit, but this is the camera that we use for data collection. We typically use an electron flux of around 30 electrons per pixel per second. And we know that's high, and that's a compromise. We can go down to 50, well, we can go to whatever electron pixels per second, but 30 is standard. The most common other ones that we get requested are 15 and 20. But if you don't let us know, we standardly do 30. So then, well, how did we choose 30? Well, something that goes along with that goes, what is our exposure time? We do anywhere between 2 to 2.5 seconds. And what's our frame rate? And that's 40 to 50 milliseconds. Typically 50 milliseconds is the most common. And so that ends up being 40 to 50 frames. What's our apex angstrom per pixel size? That's somewhere around 1.1. So then that leaves us to give us a total dose somewhere around, depending on how close we are to 30 and how close we are to 1.1. Normally, our 1.1s are a little bit shy of 1.1. We get somewhere on the order of 50 to 65 electrons per angstrom squared. Now, again, why 30? So back in the day, we did extensive tests with our K2. We used to do 8 electrons per pixel per second at 200 millisecond frame rate. So if we're now at 50, then we can go up to 32. And why 30 versus 32? Well, 30 is a nice round number. Why 50 to 65? Why not 30? Why not 20? So then if that's the case, yes, we can. It's just that we were testing for a couple years at this setting on a K2, and we had 2 years worth of test sample data to know limits and how we can reach high quality resolution reconstructions with the most efficient data collection. We just translated that to the K3 and verified. So we've had K3s for, almost a year now on some systems, and we know very well the compromises that we are getting coincidence loss, but in the sense that for at least sub 2 angstrom reconstructions, we can use these settings with super res. Without super res, we're really stuck around 2.2. Do we use super res and go sub Nyquist? Typically, if I wanted to go and get a sub 2 angstrom reconstruction, I would not do 1.1 super res. Our preference is to go up a mag, and going up a mag would mean 0.83 would be the next mag available. If we wanted to go even further, 0.65 would be available. If we were going to go for broke, we have a half angstrom and even a 0.4 angstrom. So we would rather have our physical pixel size be this and go up a mag rather than interpolate that. Doesn't mean we don't do that. There's some times when we do want to do count in super res. If we're merging data If we know we are going to be testing certain new programs, we want to do technique development, we will. But if we wanted to do data collection just for a normal experiment, for us, there would be no need, because if there was a burning need for us to get better resolution, we would just collect another data set. We have the luxury of saying that, and because we probably say we can just collect another data set, our attitude is more on going up of physical pixel size rather than interpolate that. The only time that we have done super res would be if we're particle poor and we go 1 point. So if, what's the other side of 1.1? Well, there's like a 1.3 angstrom per pixel. So something that we might do would be do a 1.3 angstrom per pixel or 1.7 angstrom per pixel. And in super res, just because we wanted a larger field of view and more particles. And in that case, we weren't really pushing for resolution. It was a compromise because of sample prep. Okay, so that was a long answer, but hopefully that answers that question. Okay. So Micah, what is your most favorite pixel size?
I usually stick with about 1.1. I think it's a good compromise between, you know, potential resolution and a decent field of view.
And is that because you use a particular size hole or grid?
Yeah, so I I've bounced back and forth between using 2 2s and 1.2, 1.3s. And if you've got 2 2s, something like 1.1, I think is enough to get 3 exposures per hole, assuming you can sort of set your spot size to not burn the next exposure over, which can really help speed up data collection, which is nice.
So at SEMC, our standard grid currently, it has changed over the years. We use different size grids, but we normally use a 1.2, 1.3, meaning 1.2 micron hole, 1.3 micron spacing. I think like 300 mesh more or less is something that's common. Way before we went to direct detectors and we were just on initial CMOS cameras, we were using either 2 1s or 2 2s, and we were 400 mesh. It was what was available. I mean, there's different supply chain issues. Does it matter to me if I'm 300 or 400 mesh? I think we would work around it. I mean, it's whatever we have the most in supply, really. There was a question on objective apertures again, and I guess we didn't really flesh it out before. Do you collect with or without an objective? So Micah, do you collect with or without an objective? I would say
it depends on the microscope.
Right.
I think at a Krios, I think it's usually out, right? I can't remember. It's been so long since I had to set up a microscope.
It's all done for you, so you don't know.
Yeah, most of the time it's done for me, especially in, well, the last year.
So typically we use 100 micron objective aperture at the imaging settings I say are standard. Well, why 100? Why not 70? Why not no aperture? What is happening? Something that we do during setup is we use a cross-grading grid, and I just pulled a random gold. I don't even know if this is the right image to go along with this, but in that paper they had the spacings for the rings you see. So normally we see 2 very distinct gold rings with standard settings with 100 micron aperture, and we barely see the third one. The third one is basically where our objective is cutting off. So what does that say? Well, we're cutting off at the 1.4. So that's usually somewhere around it. Well, can you be more accurate than this? So we do this during setup because this is an easy way to center our objective aperture. But there's an equation based upon your source and what aperture you use. What wavelengths are you cutting out? So you can see if you're trying to obtain a particular resolution and you're going through a pinhole, well, are you going to lose resolution? Well, yes, but are you going to lose resolution that will impact you? Well, if you're only trying to aim for a sub 3 or even mid 2 angstrom reconstruction, you can leave the aperture and you can pull it out and you'll get more information if you have more information. So that doesn't answer, do you recommend putting an aperture in or out? That is more of a choice. And I would have to say if you wanted to do, and that choice may not be resolution based. It might be also other factors that you're considering. Like, let's say I want ice thickness measurement. Well, if you have an energy filter, you can use the energy filter. But in a proxy, you can also use aperture limited scattering as a way to infer your ice thickness. And in that case, if you don't have an aperture, the uncertainty is greater. So it's a balance of what you want. And why I don't have one preference or the other is because for us, since we are trying to reach more moderate resolutions, I'm talking about now 2, like a couple of years ago, I would say moderate resolutions of 3, but 2, like mid 2s and 2s are more obtainable. An objective will not compromise your imaging that much because you're not blocking the frequencies that you're interested in. If all of a sudden I said, okay, we're now interested in subatomic or closer to 1, then you definitely would have to care because you'll be outright removing those frequencies if you have an objective in our standard settings. You would have to change our standard settings, either go super res or go up a mag 2 because you would also be Nyquist limited, as we just discussed. So I don't know if there were more questions about objective aperture. I would call it a preference. I don't mind putting it in or out. It's just user preference. Grids. So this is, again, more back into the sample preparation. People were asking, like, oh, what does a holy carbon grid look like? We talk about grids interchangeably with many different ideas, but when we talk about a grid for negative stain, it's just continuous amorphous carbon. When we go to cryo, we all of a sudden think of like, oh, this is what a grid should look like. And part of the discussion we had the other time, we're saying like, well, what happens if you have different form factors for grid size, spacing, even what a grid square is? Not even a square, it becomes a hexagon, etc. So this is what it looks like in an SEM. So you take a room temperature grid, and so the question is like, okay, what happens? Well, what happens in cryo? Well, people have looked at that, meaning someone has plunge frozen a grid. Many people have plunge frozen grids. We have even plunge frozen grids, and then put it into an SEM and looked at it. And it is not as pristine as you think, and there are a lot more variations than we believe. So Bob Glazer was one that was trying to figure out blotting and wicking and understand what happens, and they imaged the front side and back side. So sometimes the front side where you blot looks very pristine, but the back side could be quite uneven. And what is surface contamination? Well, surface contamination could also be uneven. And there's many references, so you can look into that. And with the advent of Cryo ET and Cryo Clem, a lot more people are looking at not only proteins, but cells, etc., on grids and seeing how normal plunge freezing affects it. The types of experiments we do in-house here are more on the right, where we have this blot-free vitrification. We have these nanowires, in a sense, like what are these nanowires doing? So there's many times when people use different modalities of EM to better understand EM, as it were. So for Cryo EM, yes. So if you're really curious in more of these SEM pictures, what does a grid look like once it's frozen? There are a lot of papers and preprints out there right now. And so these are just a few examples. So hopefully that helps. It's more uneven than one would think. When you're looking through just transmission micrographs, you have I won't say a distorted view, but it's a very different view of the grid, and you might be fooled in thinking that you have very pristine grid squares and ice looks very even. In reality, how much do we really think about this? I don't really think about it. Micah, you've seen a lot of these SEM images. Do you even think about this when you're making grids? When like what a good grid and a bad grid looks like?
Yeah, every time I see them, I think I should pay more attention to it, consider it more. But normally, no, I don't. I think there is images like this. I always think.
I get afraid. Like, oh my goodness.
Yeah, I get scared and then kind of obsessed with this idea about how to fix it, right? Like, what can I do to make the perfect grid? Can I come up with some sort of protocol that gets rid of, of this ice that sort of builds up on the grid bars and the backside of the grid and gets rid of all this scary looking surface contamination? And I think for some people, if you want to like devote time to researching that is a worthwhile thing to do if you're interested in doing research in EM method development. But if you're not, I just make grids, and if they look bad, I throw them out and I move on to the next one and I try again. Because to me, it's faster. I don't have time to devote, I guess, to these kinds of methodological questions. I use the technology that is available. I try stuff, and this is probably a theme throughout most of my answers. I try something, and if it works, great. And if it doesn't, I move on and try something else.
I think people would be shocked, like, oh, look at this wonderful data. I downloaded the Empire data set. And probably if we save that grid, took a tomogram, and put in the SEM, it might be even worse than this.
Yeah, it would look terrible.
It would look terrible. It's like, what's going on? And that's not just surface contamination due to crowd transfers. It's just what it was.
And there is somewhat related, Misha, one of our staff scientists, had done an experiment with apiferritin, this very common test protein that we like to use that routinely reaches sub 2 angstrom. And he collected some data sets on a really terrible grid, really, really poorly vitrified crystalline ice. I think even some intentional misalignments of the microscope, and then processed something like 100 micrographs of apiferritin and was able to reach still, I think, somewhere sub 3 angstrom resolution, even with bad ice, even with a poorly aligned microscope. Don't go poorly aligning your microscopes, but to me, it was an experiment that highlighted the importance of good sample biochemistry over trying to like fiddle with getting the perfect grid. If you've got something that's biochemically stable, for the most part, if you can get it onto a grid and into a good microscope, and you still you'll probably get good resolution. I mean, barring things like the sample falling apart in ice, or really significant anisotropy due to preferred orientation. These are really common problems at the sample prep stage. But for the most part, if you're on a good microscope and you get poor resolution, it's probably the sample.
I'll skip to a question on optimizing, because this is appropriate. Is to reiterate what Micah said, like if you had a perfect sample, you can make up for substandard vitrification and a microscope not being perfect. Now, if your sample is not perfect, then you want the other components to no longer hinder you, it's a big stretch. Microscopes cannot give you better biochemistry. Better biochemistry can give you better biochemistry. So I wouldn't want to put too much pressure on a microscope because it's just an instrument. But there have been a lot of papers trying to revise a workflow for a novel sample going into EM. And most of the workflows follow this criteria or this type of unidirectional pathway where you do standard good structural biology, you do negative stain, you do diagnostic cryo EM, then you do initial cryo EM data collection, then you finally do high-res cryo EM data collection. Partly, this is also being cognizant of the price point, because if you had unlimited access to, I guess in this workflow, step 5 resources at step 2, well then of course you would incorporate step 5 and step 2. But if there's a a paywall, or if there's a reason where all the high-end instrumentation are being used by the minute, and you have days on a screening microscope for negative stain, well, it's a lot easier to get and more versatility to use up a day or two for the same cost as a 1 minute on a high end, right? And there was this idea of, look, well, if going through all these steps, something fails, what is your recourse? Easy for us to say, but it really is sample preparation. And the reason why, we're not just talking about plunge freezing sample preparation, meaning as ideal as you can to get a cryo EM sample, every single step forward just works. The standard workflow, even how imperfect the grids we showed you, it just magically works out. Not to say that without effort and a lot of trial and error, you can't get through it, but it will take effort. Okay, so let's go back to a question I skipped. I just copied and pasted directly from chat. Let me see. General procedure strategy do you recommend for focusing, refocusing sample and grid when performing negative stain? For example, if you're out of focus and you're not sure if you're under or over focused and it's taking forever to refocus. So I guess this is more on microscope operations. For us, focusing is pretty automatic. The times when focusing goes awry usually is when we try to do the autofocus routine at the wrong Z height. And it's like, oh, I don't know why I just collected this square over focus. Something's wrong, I can't find focus. Usually when I go to the microscope and I find eucentric height, we're 50 microns off eucentric height, and that's why they could never find the focus properly. So something that's very simple, just first thing I always check, regardless if I'm already focused, is I try to make sure we're at eucentric focus. I just basically tilt the stage and hopefully the image doesn't move. Okay, if that's fine, then you're looking at images like, okay, well, am I over focus, at focus, or under focus? We have sample images. I think Mahira, I don't know if she's here. Do you happen, maybe you can quickly Slack me if you can dig them up, but we took some test images of what over focus, at focus, as under focus looked like. And normally when we have a microscope operator, we are at eucentric and we're trying to focus, we concurrently look at a live FFT view and we literally turn the focus more to focus. And ideally what we would see is that we would get more and more to focus. So classically, if you're doing certain things more manual, you might have a live view where you have a binned image and you're taking a live Fourier transform and you have an FFT. So then when you're actually turning your defocus knob, either the positive direction or negative direction, if you're starting out defocus, your normal image, you might see a black outline. When you're at focus, the image will look very fuzzy. And when you're over focus, you'll see sort of a white outline. In the FFT, what you'll sort of see is that as you're going closer to closer focus, the tone rings are going out. At focus, it blows out. And then when you're going over focus, they contract back in. So on your microscope, there's something that you'll see as positive focus versus negative relative to whatever you say is 0. And as you're marching one direction or the other, you should eventually reach it. So if you are completely very far out, there's something called eucentric focus. So normally when the technician or engineer initially sets up your microscope, they put in a standard grid in a particular holder. So it's holder dependent into the microscope if it's a side entry, or if it's an autoloader system, it already has a particular Z height. So then you put a holder in and they empirically find what focuses on the standard grid, and they set that as a base level eucentric focus. So if you ever get lost, you can always hit eucentric focus, you get close, and maybe you use a different holder, so there's a couple micron differential, then you would find that through that process. I don't know if that made sense, but hopefully that answers that. And what we will do is we will have to, what we'll try to do is we'll find images that Mahira was taking. That was during the practical of going through the microscope, and we'll post that online just to give you an image of what under focus / defocus, at focus, and over focus would look like. And we could even take the Fourier transform of that, and then that will show you what that looks like. So if you have more questions, then the other thing we could do is we could set up a second, a practical, in an additional practical where we go to the microscope and go to a grid and just show what happens when we're under an over focus in greater detail. And perhaps that will explain or what I'm talking about a little bit better. Do I change, if I'm reading this question properly, do I change magnification to do that? Typically, I stay at the magnification that I want to look at. Normally, when I'm focusing, the main position I'm at the same mag as exposure. So if I'm at a particular exposure magnification that would be equivalent to a 1.1 angstrom pixel size, at a particular illumination area, a particular spot size, my preference is to have my focus preset be equivalent. It might be a different intensity or illumination area, but it would be the same spot size and magnification. Okay, well then I went on, okay, good thing. This is a two-way conversation, so maybe I went on to a digression compared to what you're asking. But normally, if time is an issue, I would basically make sure auto eucentric height and then autofocus, and it should just work. If I'm having trouble and I go around different areas of grid and it's always failing, unless this grid is make or break, I would just put in another grid. So normally when we do data collection, we don't put one grid in, we put multiples. We might put in a couple duplicates. And there have been situations where no matter what we try to do on this grid, one grid square is 10 microns away from the next grid square. And then you go to the next grid square, it's 50 microns away. And that's a very challenging grid to collect on. That would imply the grid is crumpled. And unless this is like the only version of that sample you have, I would say go to your backup grid, because otherwise, if time is an issue and automation doesn't work, there's only so much you can do, because if automation doesn't work, then it's manual. So if it's more cost effective for you to do manual, then, and you have to stay on the grid, well then, I guess something is better than nothing. Okay, so we had a question on issues of cryo TM analysis of protein, its size. What characterization is needed before we go to TM analysis? That's what we were trying to say. You just need better sample. But I would say if you can get EM feedback, then it's always best if you're trying to get an EM ready sample to use EM feedback. Sounds really simple, but it's like, okay, I have a great Western blot, so it must be EM ready. I have this wonderful object of interest. I have no characterization, but it has to be EM ready. Well, if you have no EM feedback, how do I know it's EM ready until I do the experiment? So it's very simple in concept, but it might be hard depending on where you're coming from to get any EM feedback on your sample. But it's the same things like, I have a wonderful protein. This has to diffract to 1 angstrom and I must get an X-ray crystallography structure from it. I have no crystals though, but I know it has to work because my biochemistry is wonderful. It's like, well, until you get a crystal, even if you don't give me a 0.90, you might have high confidence, but at the end of the day, like, how do I know? It might be a twin crystal. There might be other considerations, even though it might look good. So that's the same thing where it's hard to give you exact steps to say how far your sample is from being data collection ready if you have no EM feedback. You can say, the only other way around it would be 1,001 people in my field have just thrown this on a grid randomly, and this quality, this metric, I should in 1 hour get this reconstruction. Okay, maybe it might take me 2 hours, and I'm maybe new to the field, it might take me a day. In that situation, because you have proxy metrics that have been proven by a variety of people, then it's a different regime. Then it'd be like, okay, like if you're in a ribosome field, this is very common. Like, okay, then I know what this protein is. I'm using the same protocol. Okay, then in that case, you would have high expectations. But if you have a new novel protein, so that's usually the case, and you have no EM feedback, I would be hard pressed to give you EM feedback, because I wouldn't know what the result would be until we get the result. And that's not a very satisfying result or experiment, because it's sort of all or nothing. Once you have the next experiment, then we can move on and do other things. We had a couple of questions. Do you recommend multi-shot data collection? So this is something that I want to clarify. And so we use several different terms. So normally we have, pretend this is a grid square. We have holy carbon. So what ends up happening on this grid square is that we have, holes that we try to collect on. And this is just to get our definitions down, because people use several different definitions. Okay, great. So now we have a particular grid with a particular hole size and spacing. We typically do what Thermo Fisher calls APHIS, or image beam data collection, or image shift. And the idea would be, so you would go to a particular location on this grid square, get eccentric height, and then you would go to a region of this grid and take a higher mag, or medium mag image rather, and you would have this particular area as an image. And then you would go, let's say, to this group of 4, get what we call focus here. So this was, you get Z height at this level, then you get focus at this level, and then you would image shift and you would collect 4. And so then per stage shift, you can get maybe, okay, in this example, 4 shots. Okay, but what happens if these are really huge holes and your beam diameter is only this big, and your sensor diameter, or sensor size, is this big? Well, then you're wasting a lot of real estate. So what you could do in that case would be what we call multi-shot, and arrange it in a way that I'm going to be taking not 1 image per hole, but I could take 4. And since in this case I have 4, I could really take 16 images. So what I'm implying is that you stage shift here because you have to get to there, and then you use image shift to then collect multiple times. Is there any difference between taking 1 image per hole, like, versus this? So there's the other extreme where you literally go to a hole by the goniometer and take an image, then you go to the goniometer to move to the other hole and take an image. No one does that because that's a long amount of time, because goniometer movements require quite a bit of time to settle. So then what's the difference between multi-shot and not multi-shot? It depends on your illumination area and the mag of the actual pixel size of your sensor. Because this works here fine, but if you're at the mag where your sensor size is this big, then you're actually going to collect a lot of support film. So like, oh, well, obvious, I want to go from here to here. What happens if this is 1 angstrom per pixel, this sensor here, and then this is 0.2 angstrom per pixel there? Well, then there's an obvious trade-off where you can collect a lot faster just by image shifting, and you can go along here versus just taking one image like this. So this is an extreme case, but this is a consideration where what's your sensor size? The other consideration, based upon your hole size, what's your illumination area? And what you want to do is your beams can overlap, but what happens if for you to get fringe-free illumination, my beam has to be this large? So in that case, microscope-wise, I can't really fit it because I'll be overlapping, I'll be overdosing this particular area multiple times. So in principle, I would say, do we want to do multi-shot? Yes. That would be faster for data collection because you can get more images for the unit time, because you won't, per goniometer movement, the ability of the microscope to image shift and collect will be a lot faster, and so you get higher throughput. But depending on what your hole size is, your support film, your sensor size, your illumination area, you might be only able to collect 1 image per hole, or maybe you can collect more, but how much more? And that's an open question. Then, well, why don't you just set up the microscope to just image, stage shift here and image shift not just this little quadrant, just image shift the whole square. And yes, you can. There is some drawbacks to that, because if you're image shifting here, well, let's say you're just image shifting like in a micron, that's not too much beam distortion. But let's say you're image shifting 5, 10 microns, there's a lot of image distortion. So there is hardware correction to minimize the coma. So what are you doing when you're going here? You're affecting coma, you're affecting stigmation, and you're affecting your defocus. And there are some hardware compensations you can go about it. And there are some software compensations. So if you can achieve this, then yes, that will be the highest throughput, because per stage shift, you can image shift here. Like, well, won't image shift also have overhead? Won't taking pictures have overhead? Yes, that has an overhead, but that overhead for image shifting and taking a picture would be a lot less than stage shifting over there and taking a picture. So if you can get good image quality, then I would say, yes, I would go for multi-shot. We would need special imaging settings to accomplish multi-shot, because again, we're worried about illumination area and sensor size. And there could be a situation when we go through certain apertures, we have what's called fringes. And if you have what's called fringe-free illumination, then you don't care, because your crossover point will be exactly where your aperture would be. And your Z height would be of the goniometer would be at a particular position where you could collect basically up to the illumination area of your beam, and that'll be theoretically the highest throughput. Most microscopes currently out there don't have fringe-free illumination, so you would have the Fresnel fringes on the edge, and you might have to have quite a bit larger beam than your sensor to actually image. So obviously you don't want your beam smaller than your sensor, it has to be larger. I would say multi-shot works categorically better if you're sub-angstrom pixels. The people with multi-shot, so if you look at the manual for TFS fringe-free illumination, is actually optimized for, I believe, a half angstrom per pixel, physical pixel. So from our standard settings, you'd be half of our standard settings. Super res would be 0.25 angstrom per pixel. So there's a trade-off, because if you are working with larger complexes, multi-shot may not be the best for you. It's a crossover point of how many images you can get versus particles versus resolution. So multi-shot tends to also work better when you have smaller proteins, because it is most effective with smaller pixel sizes currently. Can it be extended? Yes, it can be extended. It's just, I'm just thinking in specific use cases of how our microscopes are most readily set up. Can it change? Yes, we can use different alignments and try to optimize it in different settings. Moving forward. What is the main difference beyond diagnostic initial high-res data collection? It's amount of data. Usually when you're doing screening, you don't want to do data collection, because the screening is intent that you would do data collection at another time. So if you use your electron dose and image your full grid, then you have nothing left for data collection. If you're ready for data collection, so there's a difference, because we use screening poorly. So there's actual screening, meaning I have 10 samples, 10 different constructs, and maybe I did a couple of different, conditions. So now I actually have 20 different samples. There's screening as in like, okay, which of these 20 unique samples do I want to go for first? Or is one better construct / buffer than another? Versus I have the grid I want to do data collection on. I just don't know if I want to collect on this region in the grid versus that region in the grid. And people call that screening too. But the settings you use for collecting on one area of the grid versus another is the same as you're doing data collection, which is different from screening. Screening, you're normally taking fewer images, you're at a more moderate pixel size, you might be at a greater defocus, because you're not trying to create a reconstruction. You might only be getting an ab initio model, or you might be getting really nice class averages, and you want to see particle density. So you go to further defocus, and you have a more stringent envelope function where you dampen your high frequency resolution, but you don't care because you're just looking for particle distribution and overall morphology. So people tend to have different settings for screening versus data collection. And then within data collection, and sort of optimizing like what first versus last. And that is just ordering better images in and out, or just what do you think are more optimal regions? So the amount of, so answering the question, yes, the amount of data is different from screening and data collection, because data collection tends to be larger, but also your imaging settings and your imaging parameters. What is the smallest protein that we can solve by single particle? Well, okay, well, there's many papers about pushing resolution of single particle. Sub 50 kilodaltons is achievable, but I wouldn't say routine. So there are papers showing that you can do very small things. I would say 200 kilodaltons is becoming more routine. 100 kilodaltons, it'll be effort, and 50, it's going to be, you're going to really need a very good sample. I think to tease out, can we do it versus is it routine, is very important. So what is routine? Routine is usually 300 kilodaltons and above. That tends to be very routine, meaning a wide variety of labs can do that. When you get lower than that, the labs that can do that routinely become smaller and it's more effort. And then you would say, how many labs can routinely give me 3 angstrom reconstructions, 2 angstrom reconstructions of 50 kilodalton proteins of whatever I want? That is the truth that's going to come out soon enough, because that is something we're all interested in, pushing the technique. And I would say that's technique development. However, I don't feel that, though it's aspirational, and yes, it's been done in proof of concept, and that's really good in showing what we can do. But if you say, okay, yes, someone has solved, Cryo EM structures to 0.7 angstrom resolution, everyone should now be doing micro ED instead of tomography or single particle. that is a false argument. And so why do I give that extreme? Because most people, when they come to me, it's like, oh, because this is done, therefore we should all do this. And that's very odd to me because they see things in very black and white. And I would want to be more nuanced. And I would say, yes, cryo EM is good, but you wouldn't want to give up X-ray crystallography. You wouldn't want to give up NMR. You would want to do that in conjunction. So just like EM, like I would want micro ED, single particle, and cryo ET because they can solve different resolution ranges from like, small molecules to complexes to in situ. So I would want to work at it in concert. So that is sort of my opinion. So there's a lot of people that are, I guess, a little bit too drastic for my tastes. I would want to make use of all these techniques. So minimum size of 50 antibodies. Well, yes. Okay. So the question was like, antibodies are routinely solved. I would say antibody complexes are a sweet spot, how cryo EM can help. And I think that's buoyed by a lot of X-ray work in the sense that by cryo EM, we don't need to solve the full antibody at resolution. And most of the time, we don't have the full antibody. We have an FAB. And even with an FAB, we don't see the full FAB. We see really what the Fab is binding, the epitope that it's binding to. So I would say I'd be very optimistic. I'd be very aspirational, but I would say just doing a lot of FABs alone, or things under 50 kilodaltons are just very challenging. It can be done, but I would say if you can do complexes and larger things, then it'll be a little bit easier and it'll be a little bit more routine. We have a question on the focus range. Normally, the recommendation is to go as close to focus as possible. So normally, our standard settings are somewhere, sub-micron, like 0.7, 0.8 micron to maybe 2.5 micron to focus. We've had people request like 2 to 4 micron to focus. We had people request 0.5 micron to focus. Normally, when you go higher in magnification, people request the focus ranges closer to focus. We've had, that I can count, only 4 requests for no defocus range whatsoever. Most people request a defocus range. And if you've listened to some of the lectures that we record, you would know why. Because if you're actually at a particular defocus statically, and you know that there's aberrations in the microscope, you would see, if you take an image, we have what's known as the contrast transfer function, the CTF, where if you take an image, you take an FOT and you fit it to our CTF equations, you'll notice that there are certain regions with positive phase, 0 phase, and negative phase. So if you were exactly focused and you collected data, there would be certain regions where when you finally do your reconstructions, your FSC would look quite odd because you would not have no phase information or very little phase information. So why did those 4 people ask no defocus range? Well, in reality, our grid is not flat at 0 tilt. There is actually a tilt. And our grid, as you saw from some of these SEM images, it's not completely flat. There's undulations. So inadvertently, we did have a defocus range, but it wasn't done through the program, and it was done just because a grid was not flat. And no grid is actually flat. Can we talk about our experiences of just doing grid preparation? So we have used C-flats and quantifoils there, and we've actually made homemade grids. Something that we notice with very, very thin carbon, and this could also be the case where you have polycarbon and you float a layer of thin carbon on top of it. You have to be very careful about your glow discharging, because if you over glow discharge, then you get into what's called plasma cleaning, where you can remove layers, if not damage layers. So quantifoil for us tends to be a little bit thicker. So the quantifoil, so grids overall may have contamination. And so certain lot numbers you might find because of the process the grid was made, you might want to do a hydrocarbon wash like chloroform hexane, because there might be plastic or polymers on the grid that you want to remove. And then you can just chemically treat it to remove it. Most of the grids we work with, we use glow discharging, where we, in vacuum, we perfuse a little bit of gas, and we send a current, and we temporarily deposit some charge onto the grid. Air is the most common one, sometimes hydrogen, oxygen, separately, like we're very careful not to create an explosion. Sometimes argon, hydrogen, etc. So you functionalize the support film such that the drop can go onto the grid. And that can actually spread, and that helps you in Cryo EM to make these thin films. Quantifoil, since it's thicker, it's a little bit harder to glow discharge. We can actually glow discharge longer. For thin carbon, we do much shorter. Well, how long is long? How short is short? The best way to do it would be to characterize it. You can use a light microscope at high mag to do some initial characterization, but you can also put it into a TEM if you have a nice screening scope, where you can empirically determine at a particular power, wattage, glow discharge time, gas perfusion rate, well, how damaging is it to the grid? And you can just glow discharge for what you normally do. You can excessively look at it and you just pop it in, and you can look and see if there's damage to the support film. And then you would be able to calibrate. Normally we use a Solaris, and if you're curious, we can post those particular power settings on our Solaris or Solaris 2. For our normal settings where we can glow discharge a quantifoil for 30 seconds, we might, in those same settings for a C flat, only glow discharge for 7 seconds. Okay, so that's if you're talking about carbon, just really, really thin carbon. And let's say you have quantifoil, but you put a layer of really thin carbon. Why would you do that? So there's a situation where you might want to put a support film as a protective layer. So you have a wholly carbon grid. Why? Because you don't want to image through carbon, because that has noise. So that signal can be very strong. So that's why, for example, what you're seeing here, this wholly carbon grid example, we're actually imaging through buffer. So the holes are there is to help support buffer that's vitrified to hold your sample. Let's say you have orientation issues where you want to put a thin layer on top of, let's say, this quantifoil. Then you would worry about the ultra thin layer, not the quantifoil. So though the quantifoil might be very robust and hardy, and you can glow discharge it for 5 minutes on end without any issue, your ultra thin layer on top of the quantifoil might be plasma cleaned away by that time. Your graphene oxide, for example, might be gone. If you glow discharge for 5 minutes, you could be scrubbing and plasma cleaning. Okay. I have gotten to the end of my chat questions. I don't know if there are additional questions, but I'll give people a few seconds to pose them. If I missed anything, you can bring that up. Or if I give you an answer that you felt that, okay, I only gave 90% of an answer, I want that other 10%, we can finish that up. But tomorrow there won't be a journal club, because we've progressed to our lecture series to move to the next section. Because Micah's been getting an ever increasing journal club list, we're gonna now, after today, lock it off. So everyone that we've received replies saying that they want to be part of a journal club, okay, from this point on, we'll say has been locked. And then now, truly this week, Micah will send you an email list and a list to sign up for various articles. Next week, we move on to our EM crystallography section. And next week on February 1st, we'll have Bill Rice talk about micro-ED and 2D crystallography. If you do have particular questions for Bill, ideally by Wednesday, but at latest by Friday, do email Micah and myself, and we can forward them to Bill such that if he has some time to prepare or slides that he wants to prepare, he would have time to do so. If you have further questions that you don't want to pose in the chat, you can always email us and we will circle back. Lastly, homework assignments for the practicals. Micah, in addition, will be grading them. If you want to have a separate recitation that we go over the worksheets, let us know, and we can fill in the answers or our interpretation of the answers based upon what we showed you. So there can be more than one answer, but for the context of this course, we didn't talk about many different topics. So we would only expect that through this course, you would know about certain answers. Okay. So if we don't have anything else, then I'll say we'll see you next week for the EM crystallography section. And please keep those questions coming. As always, we'll post all our recorded material online. And something we'll work on for this week is to give the examples that we were saying about the mailing lists, over, at, or defocus, and any other materials that might be useful. Okay, well, have a good afternoon.